And hi, welcome back to Math 234. I am still your host, Steve Dragoo. And up today, what are we doing? We've got surface integrals. So we're upgrading surface area into surface integrals, sort of the same way that we upgraded arc length into line integrals. It'll be that same way. As a quick word of warning, this unit used to be split into 2 days. But due to changing in schedules and like losing a day or two throughout a semester, we had to condense this one down into one unit. I think it's one of the two units that suffered from that condensing. This one's a little worse than the last one though. So that said, we're not gonna hit every single example that's in this set, and also you might notice that the some of the stuff up here is a little longer than usual. Just kind of an artifact of the way the course is these days. So I am gonna do what I can to get through as much as possible, but based on my track record so far, always going a bit over on time, you know about how well we're gonna do. With that said, let's just get as far as we can. Starting with a review of some of the stuff that was in that pre-class video. Going back to that idea of arc length and line integrals, we had an equation to find ds, where ds is the differential for moving along some curve. We use d lowercase s to talk about moving on a curve, and it was just the x derivative squared plus the y derivative squared plus 1, which is like the z derivative squared, but the derivative of z with respect to itself is going to be 1, since that thing is an explicit function. Z equals f of x and y. But then we take the square root of that whole thing. And that got us the ds term that we needed for an incremental change along the curve. We want something similar for moving along a surface. So that surface is going to be given explicitly as g of x and y. We're also going to call the surface capital S as opposed to lowercase s to denote the difference between it and the curve. And it looks very, very similar. It's the x partial squared plus the y partial squared plus the z partial squared. Again, the z partial is going to be 1, since the derivative of z with respect to itself should be 1. So 1 squared still classically is 1. And then we'll put a dy dx in the end there. Now, if that surface is given parametrically, we'll get that by taking the magnitude of the cross product of the two partial derivatives. So say we've got some parametric equation r of s and t. We can take its two partial derivatives and then get the magnitude of that thing. Magnitudes often contain square roots in them. So we'll notice that if we just do the parametric equation for an explicit function, z equals g of x and y, we get the same result. So that square root of the x partial squared plus the y partial squared plus 1 is the magnitude of some cross product. In particular, that cross product is the vector xy g of xy. And then take the two partial derivatives and cross those. And there's the result that I think that we get. So that's the bonus exercise done up right here. And notice that when I leave it in its vector form, I get negative partial x, negative partial y, and then 1. And that vector is going to come back a little bit later on when we hit definition 7.14. So I made a note that like that thing's going to come back. So we'll return to it when it's relevant. I'll save that for the latter half of the class, though. We can also see our definition for surface area then can just be the surface integral of ds. And also notice that everything that we're integrating here so far are scalar functions. So at least on this first page, we're only looking at integrating scalar functions. Right, we are dealing with some vectors, but we're taking their magnitudes, which returns it to a scalar value. Cool. So far, just looking at scalars. So the surface integral is just going to be the double integral of some function times ds. And we look at it in two different ways for scalar functions, both explicitly and parametrically. Quick reminder on what we mean by an explicit function. If we're going with our three space and like the standard way that we orient stuff, an explicit function is one where z is a function of x and y. So imagine that it passes like the vertical plane test. If I can just say that without really having to describe what it is, that's what an explicit function will be. A quick example of something that is not an explicit function is a sphere, because that thing is going to fail the vertical plane test because the plane will hit on two separate curves. It'd be a top curve and a bottom curve, a top half of a sphere and a bottom half of a sphere. So spheres are not explicit functions, but we can write those out parametrically. So in the event we don't have an explicit function, we'll go to the parametric definition, which looks fairly similar. We just have to take f of whatever element that we have. And then when we change ds over into something that we can integrate, we'll need to pick the correct magnitude to multiply in. So to go over a couple of quick highlights, a surface integral is a type of double integral. So if we've got our function of x and y and z ds, notice that that's three variables, but we're only taking two derivatives. We have a double derivative. So we need to reduce our parameter count down to two in order to successfully integrate one of these things. So again, that's why we have either an explicit function where we can replace z entirely with x and y, or we have to parameterize the surface. But I think we might notice that in both of the two equations up there, we only have two variables, either x and y if it's explicit, because z gets substituted out, or s and t if we switch over to a parametric equation. Ta-da! All right, and then we can go integrate some stuff. Ryan's got a really entertaining snakes on a plane problem, which I have no idea what the cultural staying power of that movie was, but I'm sure that reference is a bit dated today. You can see though that was a fall semester 14 exam question. So that's roughly when that was relevant. Next up, there's a bunch of stuff with surface integrals of vector fields that I'm going to come back to. I want to jump ahead to just looking at surface integrals of scalar functions. We just talked about that. So let's get the scalar stuff out of the way, then we'll go back and do vector functions. And the first two examples are incredibly long and tedious, so I've done them out ahead of time. The third example we'll actually do together though. So what we want to do is compute the surface integral of z squared ds, where s is the unit sphere. And we're going to do it twice. Or we're going to look at it having been done twice. First, we're going to do it parametrically, and then I'm sure we'll do it explicitly right after that. So, the unit sphere, if I express it parametrically, remember that polar, cylindrical, and spherical coordinates are all very common parameterizations of the coordinate space. So as often as we can, we're going to use cylindrical and spherical coordinates as a base for parameterizing some object, something. So the unit sphere is just the sphere where rho is equal to 1. Right? That's the unit sphere. But then our phi and our theta variables, or phi and theta parameters, are still free to be whatever they want. So the parameterization for the unit sphere is just spherical coordinates, but with rho equal to 1. So if you wanted, you could even leave phi and theta as your two parameters, though I elected to use s and t here, just to emphasize that it's parameterization. So again, there it is. We'll use t for theta, s for phi, S is in 0 to pi, t is in 0 to 2 pi, because phi is in 0 to pi and theta is in 0 to 2 pi. And I want to use a quick argument to figure out what my fancy Jacobian looking thing is. Right, so R partial S cross R partial T. Right, I have to figure out what that is. And my goal here is to just use dV to come up with it. Right, I know dV from spherical coordinates is rho squared sine phi. So I think that ds should be equal to 1 squared sine s ds dt. ds dt. Mark that off in blue, just so that it doesn't get lost in with everything else. Right, rho here we know is equal to 1. Sine phi is sine s, because I replaced phi with s just to have the fancy parameterization. So I think the magnitude of that cross product should be sine s times 1 squared. There is a calculation that we could do. It's over here. And just look how fun it is. Here's our parameterization. The next two lines are those two partial derivatives. I then need a cross product of those two partial derivatives. And then there's a bunch of simplification that happens. Mostly it's just repeated use of the Pythagorean identity, which is sine squared plus cosine squared is equal to 1. I do it twice for theta to completely get it out of the problem. You can see all the parts where I highlighted it in orange. There's also an element where I've got to break up sine to the fourth into sine squared times 1 minus cosine squared. But then in the end, you'll notice in that second to last step, I've got all of my angles in terms of S instead of in terms of T, because again, all of the theta parts just went away by adding them all up to 1 with the Pythagorean identity. In the end, I get sine S when I take the square root of sine squared. All of this stuff is in my notes. If you're interested in how it all comes together, I'd recommend just looking at it later. Kim, we would be here all day if we tried to do this problem. It's kind of a long boy. But anyway, I can then go integrate that thing. I got 4 pi over 3. There it is. The second half, we're going to try to do this thing explicitly, which means we'll break up the sphere into its top half and its bottom half. So the positive square root and the negative square root. So notice I wrote plus or minus for z. When I take the two partial derivatives, I get the negative of what I started with. So I wrote that minus plus, just to argue that they pair up a slightly different way. And then I need to split up my surface integral into the sum of two separate surface integrals, but I'm going to call S1 and S2. One for the positive square root, one for the negative square root. And hey, look, here's a whole bunch of work. Ta-dun, da-dun, 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 da-dun. I switch to polar coordinates, I get 4 pi over 3 again. Again, I've tried to be as detailed as possible with my notes. You want to see the full computation on this problem, go back and look at the notes that are featured prominently on our course website. Let's go try one that I think is actually doable in class. Evaluate the surface integral of y ds, where s is the surface, z equals x plus y squared. So the first thing you should do in these surface integral problems is make sure you identify what the surface is, because there's often going to be multiple equations or multiple expressions happening in one of these surface integral problems. We need to identify our surface so that we can start figuring out what our Jacobian should be. Right, so we want to go make sure that we identify the surface first, which in here it says pretty explicitly, S is the surface, Z equals x plus y squared. So G is x plus y squared. And then that's the thing that I'll go take partial derivatives of. So g partial x is 1, g partial y is 2y. Once I've got my surface identified and I know what my partial derivatives are, I can go compute this surface integral. So this will be the double integral over the region S. Stop out. Whatever. That's good enough. Of y times ds. And also notice that right here I would be replacing z in my integrand if I had one, which I don't have one this time because my integrand is just y, so there's no replacement that needs to happen. But if there were z, it would be gone at this step because I need to make sure that I only have two parameters when I actually get to my double integral. And this thing should be g partial x squared, so 1 squared, plus partial y squared is going to be 4y squared plus 1. Let's do dx dy, x from 0 to 1, y from 0 to 2. And just like the surface area problems, we often end up having to integrate some sort of a square root function. So hopefully we have something that we can do u substitution for. Now I'm going to do dx first, just because it looks particularly easy. Right, the only x's I have are the dx. So this thing is equal to 1 times the integral from 0 to 2 of y times the square root of 4y squared plus 2 dy. And then we get to integrate that thing. So I think that there's a nice looking u substitution here. In particular, u is going to be 4y squared plus 2. So du is going to be 8y dy. And I already have the y dy part. So I just need to deal with that 1 over 8. Or deal with that 8, which is going to show up in the integral as 1 over 8. So 1 over 8 times that thing integrated. I'm integrating a square root function. So that's going to go to the 3/2 power, from 1/2 up to 3/2. So that means I need to divide by 3/2 or multiply by 2/3. And my inside was 4y squared plus 2. And again, that goes to the 3/2 power. And I want to evaluate this thing between 0 and 2, since those are my y bounds. And then just go plug stuff in. So 1/8 times 2/3 is 1 over 12. Times whatever I get when I plug some stuff in. If I plug in 2, see, that'll be 4 times 4, which is 16, plus 2 is 18, raised to the 3/2 power, minus whatever I get when I plug in 0, which unfortunately isn't just 0 this time, because I'll still be left with 0 plus 2 to the 3/2 power. And I would probably leave things right there. I don't see much use in trying to simplify it any further. And I guess maybe I could pull a 2 to the 3/2 out. Leave me with 27 minus 1. And if you really wanted to, 2 to the 3/2 over 12 times, I think that's 26. I really don't think that step's necessary though. Gray that out because it's not a step we're gonna ask for. But okay, I think after that, yeah, we get into surface integrals with vector fields. So just in case the unit wasn't hard enough already, we're gonna go add some more to it. So scroll back up to the part that I skipped, which started right here. So going over even more definitions. So we want to extend these integrals into vector fields. So far, let's call it 1.5 examples that we looked at, we were only integrating scalar functions. So now we want to look at trying to integrate a vector function on some surface integral, which means we need another definition, because it isn't enough to just have a surface. We need to have an oriented surface. So if we go back to thinking about Green's theorem, it was particularly important that our loops, our simple closed loops that we were integrating over, had an orientation to them. We said if we went around counterclockwise, that was the positive orientation. If we went around regular clockwise, that was the negative orientation. So we need to do the same thing with surfaces. So oriented surfaces are a type of surface that has two distinct sides. Think like just a sheet of paper is an oriented surface. It has maybe a top and a bottom side, or a front side and a back side. Oriented surfaces have two very distinct sides. I think the easiest way to really understand what an oriented surface is to look at something that's not an oriented surface. I think the most famous of which is the Mobius strip, but Klein bottle is another fun one. So if you haven't seen a Mobius strip before, here's a rough explanation of just a picture that I drew. I think in Ryan's video, he actually like cut out a strip of paper and made one. They aren't that hard to make. Just cut a strip of paper, take the two ends, twist one of them upside down, and then reconnect them. All right, so you look at that's what we've done here. If we call our points A, B, and C, D with green on top and pink on bottom, I just twist it once so that pink connects to green and green connects to pink. And then that strip no longer has two distinct sides. Because it folds over on itself, you'd think both the inside and the outside really are the same side if I go all the way around. That's the unique fancy thing about a Mobius strip. There's only one side, even though it looks like there should be two. Of course, the trick with a Mobius strip is that it must be a two-dimensional object. So really, if you take a sheet of paper, it doesn't truly become a Mobius strip because that sheet of paper is a three-dimensional object. It just has a very, 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 very thin width to it. So we can kind of ignore that part. But a pure Mobius strip, again, would be purely two-dimensional. It won't have any thickness to it. But also only has a single side. So it is not an oriented surface. Oriented surfaces must have two distinct sides. Again, just thinking about a sheet of paper usually does the job well enough. Since we need oriented surfaces, oh, that means we need to pick one to be positive and one to be negative, and we tend to go with two natural types of oriented surfaces. We'll pick one orientation for explicit functions. That'll be upward and downward, because if it's explicit, that means we have a clear top and a clear bottom. That's what makes it explicit. But we'll also look at closed surfaces. And closed surfaces don't have a clear top and bottom anymore. Instead, they'll have an out and an in orientation. So if you think about the surface of a sphere, that thing will have an outer or an outer side and an inner side, right? I can be on the outside of my sphere, I could be on the inside of my sphere. So really the important element to figuring out what orientation we should be using comes down to selecting the correct normal vector. Because our normal vector always gets a plus or minus on it. Because my normal vector could either go in one direction or in the backward direction. So we'll just need to make sure that we pick the right one for our orientation. So to throw yet another definition at you, we call a surface closed if it's the boundary of a solid. So quick overview of what the difference between a surface and a solid. It's right over here, and I highlighted the parts in the equation that make the difference. In both cases of those two equations, I'm looking at a sphere, but in one, x squared plus y squared plus z squared is equal to 1, and in the other, x squared plus y squared plus z squared is less than or equal to 1. So the less than or equal to part makes the thing a solid because now it has depth to it. It is the entire ball. It's both the inside of it and the surface of it, right? It is a solid ball. As opposed to the surface, x squared plus y squared plus z squared equals 1, that's only the thin outer shell of that ball or of that sphere. Right, so the surface, again, is just the outer shell of some solid object. Solid object being all of the parts that are less than or equal to it. And we'll say that our outward orientation is the positive orientation. So to just come over here and throw a few pictures on the screen of what we mean by positive and negative orientation. Again, for explicit surfaces, these by definition will not be closed surfaces. All right, if we're going explicit, that thing can't be closed because it's got to have a clear top and bottom. But that also means it's the easiest one to decide your orientation. Your normal vector will have a positive z component if it's upward, and it'll have a negative z component if it's oriented downward. Again, up will be positive, down will be negative, which is pretty clear just based on the z-axis. Right, up is positive, down is negative. For closed surfaces, that's where we need to go with in and out. So if you look at these two spheres and the normal vectors that go around it, some of those normal vectors that point out will point up while some point down. Some point left, some point right. Some point forward, some point backwards. But all of them point out of the surface. That's the unifying idea behind picking that orientation. Every normal vector points out, or every normal vector points in. For a sphere, they get the sort of special circumstance where all of its inward pointing normal vectors point directly at the origin. And I suppose all of its outward pointing normal vectors point away from the origin. Yeah, but I digress. Cool. So we need to find a bunch of normal vectors in order to pull this thing or to orient our surfaces, which is convenient because that's exactly what we need for a surface integral. If we've got the surface integral of a vector field, ds changes to a vector quantity to match the fact that it needs to be dotted into a field, which oftentimes gets written as f dot n times the ds that we had already calculated. So again, I'm going to use capital N to represent a unit normal vector, because that's consistent with what the WebWork notation uses. I think they tend to go capital N for unit normal vector and just a lowercase n for a not necessarily unit normal vector, which differs a little bit from how it's written in the notes, but that'll be fine. So again, surface integral of f dot ds is going to be the dot product of the field with a vector that is normal to the surface. So we're going to be looking to collect normal vectors. To simplify that a bit, that unit normal vector has a value, at least if it's a parametric equation, which remember even the explicit function can be written out parametrically, of the cross product of the two partial derivatives divided by the magnitude of the cross product of the two partial derivatives. But a rather handy simplification comes out when I multiply the unit normal vector with ds. Because remember that ds already has the magnitude of partial s cross partial t baked into it. That magnitude is a part of ds. So when I multiply those two together, the unit normal vector with ds, I get the magnitude of that cross product twice. Once in the denominator from the unit normal vector and once in ds. So those two things, effectively cancel each other out, right? They both multiply to 1. Which means practically, when we're actually doing one of the integral problems, we just need to take the cross product of partial s with partial t. We find our parameterization, two partial derivatives, take the cross product, and that gets us our normal vector. So don't forget, if I take two partial derivatives of a surface and then take their cross product, I get a normal vector. We did that all the way back in tangent planes, which is unit 14.4. So, yeah, normal vectors. That's what we get by crossing the two partial derivatives of the parameterization. Couple of other things that I should mention. This surface integral of a vector field f dot ds, also having a vector quantity, is also called the flux of f across s. So we kind of brought up flux earlier when we did Green's theorem part 2, though technically that part didn't really count because that's like two-dimensional flux. So I think I called it flow instead of flux just to differentiate between the two. But this is now proper three-dimensional flux. So if you've seen a physics class that is calculus-based, you've probably seen this integral before. So flux, again, it's the surface integral of a vector field through some surface. And also, right at the beginning, I said that one cross product that we did explicitly was going to come back when we got to definition 7.14. That's this one. The explicit normal vector, negative g partial x, negative g partial y, positive 1. And that's the way I remember this normal vector. I know that in other contexts, it tends to get written positive gx, positive gy, negative 1. But I don't usually like that one as much because that other one, the one I just said, positive gx, positive gy, negative 1, that's a negatively oriented normal vector. Because we generally take up to be the positive orientation, down to be the negative orientation. So the only term that matters for the orientation of a surface is the z component of the normal vector. So I choose to write it out with the positive orientation as my default choice, which is this thing. Notice that each of these normal vectors has a plus or minus attached to them, which all comes from the orientation that we select. Positive for a positive orientation or negative for a negative orientation. Probably didn't need to go over that part explicitly, but hey, I think you got it. So for the simplest example that we'll see today, calculating the surface integral of a plane. Here's what we have. We don't even need to jump to the partial derivative stuff because I think we know that we can find the normal vector of a plane. In particular, if my plane is just z equals 2, I have two options for the normal vector, either 0, 0, 1 or 0, 0, negative 1. But I could still plug in those partial derivatives in order to find gx and gy. 2 partial x is 0, 2 partial y is 0. And of course, we get just 1 for the third component. Also, in the vector field x, y, z, because my surface is z equals 2, and that's what I'm integrating over, I replace z with 2 because I know z is equal to 2. So xy2 dot 0, 0, 1 just gives me the integrand of 2, and then integrating that is very, very straightforward. Well, we're not here for the easy problems. We're here for the ones that make us cry a little. So let's go try one of those. All right, find the upward flux across the portion of the plane x plus y plus z equals 1, and inside the cylinder, x squared plus y squared equals 1. So again, the first thing that you should do is identify your surface on each one of these problems. There's going to be several equations in all of them, and identifying the surface is the most important first step. So, three equations. I've got F equals x, y, z. I've got the plane, x plus y plus z equals 1, and the cylinder, x squared plus y squared equals 1. So, it's never F because that's the field. The field's not the surface. The field is the thing that we're integrating. So, our surface is never going to be F. We are looking for that flux across the portion of the plane. X plus y plus z equals 1. So that's the line that's telling me what my surface is. That line is telling me my surface is the plane. Inside the cylinder just tells me what my integration region is going to look like. So this part here, this will come up for the bounds of our integral. But for finding our surface, again, I think it should be this bit over here. So I've got G is equal to 1 minus x minus y. I think that that thing is my surface. Keep that going. G partial x is -1, and G partial y is also -1. So let's go and integrate a thing. So what we're after, and in fact, let me just go use copy and paste to my advantage. Where did you go? Right here. We have an explicit surface, so I can just use my explicit surface equation, which will be this guy. I also think I want to just scrunch you in a little bit, so I've got a little more space to work with. So what do we want? We want the double integral of this thing, which looks like the field is x, y, z. So that's going to be x, y, 1 minus x minus y. Dotted with my normal vector. And we want the one that has an upward orientation. Right? We need the upward option here. So that's negative, -1, negative, -1, +1. If we go to our formula. We're still integrating over some region D. This is going to be dA. And it'll be that cylinder that tells me what D is. Also, maybe just as a quick aside, I don't really think we needed a fancy formula to find our normal vector this time, since we just have the equation of a plane. Don't forget, if I have the equation of a plane, I can read its normal vector directly from the equation. This thing is x plus y plus z equals 1, so that normal vector is 1, 1, 1. All right, so we only need to go to that formula when we need it, which is most of the time, to be fair. But if we have a plane, that thing has a known normal vector. Right? I just go to normal vector for a plane instead of needing the fancy formula. But you'll see that if I follow said fancy formula, I get the same thing. Also notice -1, -1, -1. would be the downward oriented normal vector. But all right, let's go and try and integrate this thing. Which upon simplifying that dot product, what do we get? We'll get x plus y plus 1 minus x minus y. Might as well write that all out. 1 plus x plus y plus 1 minus x minus y dA over the region D, which is the double integral over the region D of 1 dA. Right, most of that simplified. And then I just need the double integral of dA over the region, which don't forget, that is just the area of the region. Our cylinder was x squared plus y squared equals 1. We're inside that thing, so that's a circle with a radius of 1. So the answer is just pi. Yeah. All right. I think we've only got 2 more, so there's a slim chance we finish both of these in 8 minutes. You said, setting up a second verse in a comedy song. So unless otherwise specified, assume your closed surface is always oriented positively. So we're going to try to integrate over a closed surface. That's this mess right here. So you'll notice what I've done. Let me just spread these out a little bit because I know I'm going to run out of space. I've taken my closed surface, which is the region enclosed by the paraboloid and the plane z equals 0, and split it up into 2 surfaces. Because the way that my surface was described to me, it was given by 2 surfaces anyway. So in order to solve this thing, I need to look at the outward flux across 2 different surfaces. Let's give that thing a shot. If I go look at surface number 1, call you S1, and its outward pointing normal vectors all are going to look like this. Outward, or out is up on surface number 1. But if I look at surface number 2, which I'll call S2, and actually I'm going to move S2 up there, outward along this surface means down. Out equals down. So my normal vector is going to need to change between the 2 surfaces. Both of them are given explicitly, so I could just solve for them real quick. This normal vector across the first surface, remember that's the paraboloid, 1 minus x squared minus y squared. That'll be negative 2x, negative 2y, positive 1. And it looks like that was not the best place to try to write that. So how about I move you over here? For the other surface, which is just the plane as z equals 0, that thing has a normal vector of 0, 0, 1. Remember that this surface is oriented down in order to be out, because out changes as I move around my closed surface. So on the second surface, the normal vector should be 0, 0, negative 1. So let's go calculate some flux. Now that we have our 2 surfaces identified, suppose I can also come over here and maybe draw some highlights to just further emphasize. Those are my two surfaces. So we've got a thing to do. The first bit is to notice that the integral over the surface S of f dot ds is equal to the surface integral over S1 of f dot ds, where that's going to change to be the value along S1. Maybe call that ds1. Plus the double integral across surface 2, or the surface integral across surface 2 of f dot dst. Right, both of those elements are going to change on the two different surfaces. But this is now something I can go write out. No way, we are going to run out of space. Maybe shrink that a little bit, slide it up some. Okay, this is the double integral over the surface S1 of the field, which I should go remind myself what that was, yxz. So this will be yx 1 minus x squared minus z y squared. Stop that. Dotted with, well, we'll shrink this down later when we can. Dotted with that normal vector, which was 2x, 2y, 1. Yes. Don't be like that, big meanie. Okay. Shrink that a little bit. I think I'll also slide this as far to the left as I'm able. Yep. Plus another double integral. Another double integral. So that our field now is going to still be y, x, z. But z now is 0. Dotted with my other normal vector, which is 0, 0, negative 1. Yes. And this integral goes over S2. So if I go to write this whole mess together, this is going to be the double integral over S1 of 4xy. I'll get y times 2x plus x times 2y. 2xy plus 2xy is 4xy. Plus 1 minus x squared minus y squared dA plus the double integral, or the surface integral, over S2 of 0. There's nothing really to that one. Maybe scrunch this stuff together a little bit and give myself enough room for one more line. Yep, just barely. So now I've got to integrate only that first part. But in order to do that, I am going to need to change over to polar coordinates. Because the thing I'm integrating over is a circle. So this will look like 4r squared cosine theta sine theta plus 1 minus r squared times dA, which is r dr d theta. Theta between 0 and 2 pi, r between 0 and 1. And we're going to lightning round integrate that thing. Cosine theta sine theta, that's a symmetric function. Every single quadrant will have the sine times cosine is positive in 2 quadrants. and negative in the other two quadrants. So that thing integrates to 0. Don't need to worry about the rest of it. Up next, 1 minus r squared. Don't forget to multiply by r. So that's really r minus r cubed, which will integrate to 2 pi times 1 over 2 plus 2 pi times 1 over 4. Both of those 2 pi's come from the theta part. So in the end, that thing is just pi over 2. Yeehaw. All right, so quick remark in the flex definition. We can interpret that as summing up the movement of particles through a vector field. Or moving particles that are induced by a vector field that move across S. So the idea behind flex is that I've got these vector field lines that are all passing through some surface, and flex basically just adds all of those vector field lines up and comes up with a value. That's what flex looks at. Popular in electromagnetism, I think. And yeah, cool. Like I said, there was no shot we were getting through all of this during class time. So I know I'm once again out of time because honestly, who's shocked at this point? But since no one's coming into this classroom after us, I will finish this problem here for anybody that wants to stick around. But if you are done with surface integrals on this Friday, I don't blame you for leaving now. Plus, this last problem kind of sucks anyway. But for anybody sticking around, let's try to integrate this thing. So what do we have? We're looking for the outward flux of a vector field. It's zyx. And we're going to parameterize that surface. Oh, hey, look, it's a sphere. It's going to be parameterized by r of s and t, where s is cosine t sine s, or x is cosine t sine s, y sine t sine s, and z is cosine s. T is from 0 to 2 pi. S is from 0 to pi. You might recognize that as just the unit sphere. Right? It's just spherical coordinates, but with 1 plugged in for rho. And the problem conveniently gives us a whole lot of integration hints because otherwise the problem takes a while. But let's start by just writing this integral out. So I would like to integrate something over the surface S. Actually, I think we have bounds that we can plug in. So let's just go do some stuff. I want the dot product of my parameterization. Z is cosine S. Y is sine T sine S. And X, which comes last, is cosine T sine S. And here I just wrote it so that all of my T's would come first. I need to take the dot product of that with RS cross RT, which fortunately we're given the hint about what that's equal to. It should be cosine T sine squared S. Cosine T sine squared S. Sine T sine squared S. And sine S cosine S. I'm going to write a cosine S sine S just to stay consistent with being different. Slap a dt, ds on the end there, and then I'm going to come through and highlight all my angles just to be clear about what's what. These guys are green. These guys are blue. That guy should have been green. Hopefully I got them both. Nope, I only got one of them. Blue and green. Said and green, you jerk. Oh boy. Don't do that. Come back. I don't even know what I hit. Okay. Is that all of them labeled? Oh, nope, missed one. Okay. There we go. All of our angles color coded so that they're a little easier to see what's what. I have bounds now for this thing. I'm doing dt first. That's 0 to 2 pi. ds second. That one's 0 to pi. Okay. I need to take that dot product and hope for the best. So, across. Okay, across the first bits that are multiplied together. Actually, you know what? Why don't we just copy and paste some stuff? Let's see how well this works. It's either gonna go great or kind of really bad. Don't really need those anymore. All right. Taking this dot product. I have cosine t, come back here, cosine t sine s squared times cosine s. That was my first term. Plus, the second two bits multiplied together. I've got sine t sine s times sine t sine squared s. So all together, that'll be a sine s cubed and a sine t squared. Plus goes right there. I am now done with that part. We combined them. Then I've got to multiply these parts, cosine t times sine s times cosine s times sine s again. So the two sines multiply together to get sine squared. Brilliant. We got a thing. Let's again scrunch that down a little bit and call this thing dt ds. We go from 0 to pi for s and from 0 to 2 pi for t. And we start integrating, which is not as bad as it looks, because it does look kind of bad. Notice that if I do my theta integral first, I get to simplify a lot of stuff, right? There aren't that many t's. So the theta integral looked like it'd be easier. So I'm going to integrate cosine, just cosine t over its full period. That's 0. So that first term doesn't matter. Plus sine squared t over its full period. That's a known value. It's pi. I think that was even provided in the hint on this one. All right, so that's exactly half of a rectangle with a height of 1 and a length of 2 pi. We still have our sine cubed s, though. While we're right here, remark that we're still integrating from 0 to pi. And on the third part, once again, I am integrating cosine t, just cosine t, over its full period, which will once again work out to 0. Right? If you think about the graph of cosine, it has exactly as much area above the x-axis as it has below the x-axis. And then ds is still left over here. And then the final hint that we need is that sine cubed integrated from 0 to pi goes to 4/3. Right, that's the last bit right here in that hint. Integral of sine cubed u du is 4/3. This thing is equal to pi times 4/3 or just 4 pi over 3, which conveniently I think is the volume of this sphere. More on that in the next unit, which will be Monday. Okay, cool. Thanks for sticking around. Uh, we again knew we'd be going over on time. There's no surprise there. Yeah, that's it for me. Okay, bye, bye, bye.